Hello, I'm Ricardo, a software engineer at Apple. Today, I'm going to show you new capabilities that you can adopt when using Metal to render immersive content on Apple Vision Pro. Last year, we showed how to take advantage of Metal, Compositor Services, and ARKit to create immersive experiences by directly rendering your content on Vision OS. You can either implement a fully immersive experience like in Demio by Resolution Games, or you can adopt the mixed immersion style to show your content along with the real world. And now, because of valuable feedback from developers like you, Metal Rendering on Vision OS supports exciting new features. You'll be able to add even richer details and interactive effects to your apps and games. I'll explain all about the new Compositor Services capabilities in this video. To get the most out of it, you should be familiar with the Compositor Services framework and with Metal rendering techniques. If you haven't used these technologies before, you can learn about them in these previous videos. To adopt the new features, first, you'll need to make some changes to your existing render loop. I'll explain how to adopt new APIs that make the pipeline more flexible. Once you've done that, you'll be able to add hover effects to highlight the interactive elements of your app. You'll also be able to dynamically adjust the resolution of your rendered content. There's a new progressive immersion style that lets people adjust their immersion level with the digital crown. And you can use your Mac to render immersive content directly to Vision Pro. It all begins with the new render loop APIs. Let's dive in. A Metal immersive app starts in SwiftUI, where you create an immersive space that holds a compositor layer. The layer provides a layer renderer object for using your render loop. You query frames from the layer renderer. From each frame, you get drawables, which contain textures you use to render your content. If you've already created a Metal immersive app, you are querying a single drawable for each rendered frame. This year, Compositor Services has a new Query Drawables function that returns an array of drawables. Based on system context, this array will contain 1 or 2 drawables. Most of the time, you'll get a single drawable. However, whenever you're recording a high-quality video with Reality Composer Pro, a frame will return 2 drawables. You can identify the drawables with the new target property. The one for your Vision Pro display has the built-in value, and the one for your recording has the capture value. To learn how to capture high-quality videos, take a look at the developer documentation. This render frame function may be familiar to you. After querying the next frame and updating the scene state, I call the query drawable function. Then I wait for the optimal input time and I render the scene to the drawable. Now, instead, I replace query drawable with query drawables. I make sure the array isn't empty and I render my scene to all the drawables. Xcode includes a handy template that shows how to create a Metal immersive app. It's a great starting point. To check it out, start a new Xcode project for a Vision OS app and choose Metal 4 on the Immersive Space Renderer pop-up menu. Note that Metal 3 is still fully supported this year, and you can use it on the Xcode template by selecting the Metal option. You can learn more about how to adopt the latest version of Metal in Discover Metal 4. Once you've adopted the new Query Drawables function, you'll be able to use all the new features this year, like adding hover effects on the interactive objects of your scene. With them, the person using your app can see which objects are interactive and can anticipate the targets of their actions. The system will dynamically highlight the object the viewer is looking at. For example, a puzzle game can emphasize the pieces that can be selected by the player. Imagine an app that is rendering a scene with several 3D objects, but only some of them can be interacted with. I want to make sure the hover effects only apply to the interactive objects in my scene. When an object is not interactive, it's not tracked, and it doesn't have a hover effect, so I render it normally. On the other hand, if an object is interactive, I add a new tracking area to the drawable. Note that I need to assign a unique object identifier to each tracking area that I register. Then I check if the object should have a hover effect. If it shouldn't, I draw it with the tracking area render value. This is useful for detecting pinches on my objects. But if the object has a hover effect, I configure it on the tracking area before rendering. In code, I need to configure my layer renderer to use hover effects. I set the tracking area's texture to use an 8-bit pixel format. It supports up to 255 concurrent interactive objects. I make sure my layer capabilities support the format, and I set it in the configuration. In the tracking area registration code, I check if the object is interactive, and if it is, I register a new tracking area in the drawable with my object identifier. Be sure to keep track of unique identifiers for the life cycle of your objects. Then I check if the object has a hover effect, and if so, I add it with the automatic attribute. This means the system will automatically add a hover effect when the viewer looks at the object. Finally, I render it. With Compositor Services, the drawable provides several textures your app can use to render content. You might be familiar with the color texture, which is what the viewer of your app sees. There's also the depth texture, where darker colors indicate objects that are farther from the viewer. The system uses this texture to make your display content more accurate as the viewer moves around the scene. This year, there's also a tracking areas texture, which defines the different interactive regions in your scene. A drawable provides you the color and depth textures. Now you can also query the new tracking areas texture. In it, you draw distinct areas corresponding to your interactive objects. With hover effects, when somebody looks at an interactive object in your scene, the system uses the tracking areas texture to find the corresponding region and applies a hover effect on the matching part of your color texture. Here again is the object render function with my configured tracking area. To render to the tracking area's texture, I need a system-computed render value. I declare a local variable to store it, and I get it from my corresponding tracking area. If my object is not interactive, I can use the default nil render value. Finally, I pass it to my drive function, where I'll send it to the fragment shader. Let's have a look at the shader code. The fragment shader output has a tracking area render value, mapped to the color attachment at index 1. I have set my tracking area's texture there. I have bound the render value to my uniforms struct, and I return it in the shader output, along with the color value. Now my app has interactive hover effects. There's one more thing to keep in mind if you use multisample anti-aliasing or MSAA. This technique works by rendering an intermediate higher resolution texture and then averaging the color values over a sampling window. This is usually done using the multisample resolve option on your target texture store action. You cannot resolve the tracking area's texture in the same way you resolve a color pixel. Doing so would average your render values, resulting in an invalid scalar that doesn't correspond to any tracking area. If you use multisample resolve for your color, you have to implement a custom tile resolver for the tracking area's texture. You can do this by using the don't care store option with a custom tile render pipeline. A good strategy is choosing the render value that appears most frequently in the sampling window on the MSAA source texture. For an in-depth review of hover effects, including how to use them with MSAA, You can read rendering hover effects in Metal immersive apps in the developer documentation. Tracking areas also allow your app to handle object interactions in an easier way than before. Spatial events now include a nullable tracking area identifier. I use this identifier to see if it matches any of my scene objects. If I find a target object, I can perform an action on it. I have improved the interactivity of my app with hover effects. The person using my app can clearly see which objects are actionable and which one will be activated when they pinch. And this makes handling input events easier than ever. Now you can also draw your content at even higher fidelity than before. By using dynamic render quality, you can adjust the resolution of your content based on the complexity of your scenes. First, I'll recap how foveated rendering works. In a standard non-foveated texture, the pixels are evenly distributed through the surface. With foveated rendering, the system helps you draw to a texture where the center has a higher pixel density. This way, your app uses its computing and power resources to make the content look better wherever the viewer is most likely to be looking. This year, you can take advantage of dynamic quality for foveated rendering. You can now control the quality of the frames rendered by your app. First, you need to specify a maximum render quality suitable for your app. This sets the upper limit for your app's rendering session. Then you can adjust the runtime quality within your chosen range based on the type of content you're displaying. As you boost the render quality, the high relevance area in your texture expands, leading to a larger overall texture size. Just a heads up, increasing the quality also means your app will use more memory and power. If you're rendering text or user interface elements, you will benefit from setting a higher render quality. But if you're showing a complex 3D scene, you might be limited by computing resources. To make sure your app runs smoothly, you need to find a balance between high-quality visuals and the amount of power your app uses. You can use instruments to analyze your app's real-time performance. And you can use the Metal debugger to deep dive and optimize your Metal code and shaders. Remember, it's important to profile your app with your most complex scenes to make sure it has enough time to render its frames at a steady pace. Check out the developer documentation to learn more about optimizing your Metal rendering apps. In this code example, I have profiled my app and have determined that I want to render my app's menu with a 0.8 quality. This way, the text will look crisper. I want to render the world with a 0.6 quality because it's a complex scene. I also added a computed property with the maximum render quality that I'm going to use. And here's my layer configuration. Dynamic render quality can only be used with foveation, so I check if it's enabled. Then I set my maximum render quality to the value from my computed property. Remember to set it at the minimum value that makes sense for your content. If you don't, your app will use more memory than it needs to. When I load a new scene, I call my adjust render quality function. Adjusting the render quality is only possible if foveation is enabled. I switch over my scene type and I adjust the render quality accordingly. Transitioning between quality values takes a bit of time rather than being instant. The system makes the transition smooth. With dynamic render quality, your highly detailed scenes will really shine. The higher resolution of your rendered scenes can really help with the clarity of your finer details. But remember, you may need to lower the quality during very complex scenes. You can now adjust your app's render quality for your content. New this year, your Metal app can be rendered inside a progressive immersive portal. With the progressive immersion style, people using your app can control the immersion level by rotating the digital crown. This mode anchors them to the real environment, and can help them feel more at ease when they're viewing complex scenes with movement. When you're viewing a metal app in the progressive immersion mode, the system only renders the content that's inside the current immersion level. Here's an example scene from a game being rendered at full immersion. And here's the same scene rendered at partial immersion, after the viewer has adjusted the digital crown. Compare the two scenes and notice how you can save computing power by not rendering the highlighted area outside the portal. That part is not visible, so it's not necessary to render it. New APIs allow you to use a system-computed portal stencil to mask your content. This white oval shows the corresponding portal stencil. The stencil buffer works as a mask to your rendered scene. With it, you'll only render the contents inside the portal. You can see that the scene you're rendering doesn't have a smooth edge yet. The fading is applied by the system as the last step on your command buffer, resulting in the scene that the viewer sees. In order to use the stencil to avoid rendering unnecessary content, first you configure your compositor layer. Make sure your desired stencil format is supported by the layer capabilities and set it on your configuration. To apply the portal stencil mask, you need to add a render context to the drawable with your command buffer. Drawing your mask on the stencil will prevent any invisible pixels from being rendered. You also have to end the encoding through your render context, instead of directly ending your command encoder. This way, the portal effect is efficiently applied over your content. In my app, I create an immersive space in SwiftUI, and I add the progressive immersion style as a new option to my list. The person using my app can switch between the progressive and the full styles. I configure the layer next. First, be aware that the progressive immersion style only works with the layer layout. I specify my desired stencil format to 8 bits per pixel. I check that the capabilities support this format, and I set it on my configuration. I also set the sample count to 1, since I'm not using MSAA. If you use that technique, set it to the MSAA sampling count. In my renderer, I add a render context to the drawable. I pass the same command buffer I will use for my render command. Then I draw my portal mask on the stencil attachment. I selected a stencil value that I don't use in any other stencil operations. I set the stencil reference value on the render encoder. This way, my renderer won't draw the area outside the current immersion level. After rendering the scene, note how I end the encoding on my drawable render context. To see a working example of a renderer using the progressive immersion style, choose the progressive option in the visionOS Metal App template. That will get you started building a portal style metal app. Finally, let's explore macOS spatial rendering. Until now, I've been talking about building native immersive experiences on Vision Pro. This year, you can use the power of your Mac to render and stream immersive content directly to Vision Pro. This can be used to add immersive experiences to existing Mac apps. For example, a 3D modeling app can directly preview your scenes on Vision Pro, or you can build an immersive macOS app from scratch. This way, you can make complex immersive experiences with high compute needs, without being constrained by the power usage of Vision Pro. Starting a remote immersive session from a Mac app is really easy. When you open an immersive space in macOS, you'll be prompted to accept the connection on Vision Pro. Do that, and you'll start seeing your Mac-rendered immersive content. A typical Mac app is built with SwiftUI or AppKit. You use either of these frameworks to create and display windows. The system renders your window content with core animation. You can adopt a variety of macOS frameworks to implement your app's functionality, and the system displays your content on your Mac display. To build a Mac-supported immersive experience, you'll use the same familiar frameworks that allow you to create immersive visionOS apps. First, you use SwiftUI with the new Remote Immersive Space scene type. You then adopt the Compositor Services framework. You use ARKit and Metal to place and render your content, and the system directly displays your immersive scene on Vision Pro. The macOS Remote Immersive Space hosts the compositor layer and the ARKit session, like a native visionOS app does. They seamlessly connect to your Vision Pro display and sensors. In order to connect your ARKit session to visionOS, there's a new Remote Device Identifiers SwiftUI environment object that you pass to the session initializer. This is how a Mac immersive app is structured. I define a new remote immersive space, which contains my compositor content. I'll show how it uses the compositor layer in a bit. On Mac, only the progressive and full immersion styles are supported. In the interface of my Mac app, I use the new Supports Remote Scenes environment variable to check if my Mac has this capability. I can customize my UI to show a message if remote scenes are not supported. If they are supported and I have not opened the immersive space yet, I can launch it. The last part of my app is my compositor content. It has my compositor layer and my ARKit session. I create and use a compositor layer the same way I did on visionOS. I access the new Remote Device Identifier SwiftUI environment object and pass it to the ARKit session initializer. This will connect my Mac's ARKit session to Vision Pro. Last, I start my render loop like I would on a typical Metal immersive app. ARKit and the word tracking provider are now available on macOS. This allows you to query the Vision Pro location in space. Just as you would in a native immersive app, you will use the device pose to update your scene and drawables before rendering. A macOS Spatial app supports any input device connected to your Mac. You can use keyboard and mouse controls, or you can connect a gamepad and handle its input using the game controller framework. Additionally, you can use pinch events on the interactive elements of your immersive scene by using the onSpatial event modifier on your layer renderer. New this year, you can also create SwiftUI scenes from an existing AppKit or UIKit app. This is a great way of adding new immersive experiences to existing Mac apps. You can learn more about how to do this in What's New in SwiftUI. It's common for rendering engines to be implemented in C or C++. All the APIs I have explained have native equivalents in C. The C types for the Compositor Services framework start with the CP prefix. They use similar patterns and conventions as familiar C libraries such as Core Foundation. For ARKit, the C device property gives you a C-compatible remote device identifier. You can pass it into your C framework and initialize your ARKit session with the createWithDevice function. Now you have all the pieces to use your Mac to power immersive content on Vision Pro. I'm excited to see how you use these new capabilities to augment your immersive apps. They allow for better interactivity, higher fidelity, and the new progressive immersion style. And I can't wait to see what you do with the new macOS Spatial capabilities. To learn more about how to take your immersive apps to the next level, check Set the Scene with SwiftUI in visionOS. And for an overview of other platform improvements, see What's New in visionOS. Thank you for watching.